Good day. This is MEG 224, Engineering Mechanics, Dynamics, Lecture 6, Planar Kinematics of a Rigid Body, Part A. This can be found in Chapter 16 of Engineering Mechanics, Dynamics by R.C. Hibler. The lecture objectives. The objectives of this lecture, that's part A, is to classify the various types of rigid body planar motions and then to investigate the rigid body translation and angular motion about a fixed axis. Planar rigid body motion. Planar motion of a body occurs when all the particles of a rigid body move along paths which are equidistant from a fixed plane and from one another. They are like gases that move randomly. There are different types of rigid body planar motion. In order of increasing complexity, they are translation, curvilinear, rotation, and general plane motions. The general plane motions is a combination of translation, curvilinear, and rotation. Translation. This type of motion. This type of motion occurs when a line in the body remains parallel to its original orientation throughout the motion. Here, we see that when the body moves from this left side to the right side, 2 points were identified on the body. And those 2 points, the lines were parallel to each other. They are not meeting each other. When the paths of motion for any 2 points on the body are parallel lines, the motion is called rectilinear translation, as shown here. So if the paths of motion are along curved lines, which are equidistant, the motion is called curvilinear translation. This is an example. The body moves and then can move even concave wise or even in a circle, or but the path of these points must be curved. Rotation about a fixed axis. When a rigid body rotates about a fixed axis, all the particles of the body, except those which lie on the axis of rotation, move along the circular path, as shown in figure C. Here, when this body rotates, all the particles will rotate about this fixed axis, except the particles that are lying along this axis. General plane motion. When a body is subjected to general plane motion, it undergoes a combination of translation and rotation. So here, the body can rotate as well as translate. So it can translate as well as rotate. That is general plane motion. The translation occurs within a reference plane, and the rotation occurs about an axis perpendicular to the reference plane. In the following sections, we will consider each of these motions in detail. Examples of bodies undergoing these motions are shown in the figure. Here, we have this rotary disc, and then we have this crank arm, we have this reciprocating arm. Here, this point is going through a rectilinear translation because it is restricted up and down, so it can only go left and right in the x direction. So, but this connecting rod will go in general plane motion. This end will be going straight line, while this one will be rotating with the rotating disk. And this rotating disk is rotating about a fixed axis, just like this rotating arm. Then this arm here, connecting rod or arm, is going through curvilinear translation because it will come down through this curve, round like that. So consider a rigid body which is subjected to either rectilinear or curvilinear translation in the XY plane as shown in the figure. This is a rigid body. This is a rigid body. So position, the location of point A and B on the body are defined with respect to X, Y reference frame using the position vector RA and the RB. RA is the position vector of point A, and that's the distance from A to O, while RB is position vector of B, which is the distance from B to O. And then RB will be RA plus RB with respect to A. The translating coordinate system, X prime, Y prime, is fixed in the body and has its origin at A, hereafter referred to as the base point. The position of B with respect to A is denoted by the relative position vector R B slash A, R of B with respect to A, RB slash A, that is R of B with respect to A. By vector addition, RB is equal to RA plus RB with respect to R of B with respect to A. So RB is equal to RA plus RB slash A. Velocity. We know that velocity is a time rate of change of displacement. So a relationship between the instantaneous velocities of A and B is obtained by taking the time derivative of this equation, which yields that VB is equal to VA, then d dt of RB of A. So here, VB or VA and VB denotes the absolute velocities, since these vectors are measured with respect to the fixed axis, X and Y axis. The term, the d dt of RB of A is equal to 0. Since the magnitude of RB of A is constant by definition of a rigid body, so a constant where you take the time derivative of constant gives you 0. And because the body is translating, the direction of RB of A is also constant. If the body is rotating, then at every point, theta, at every angle, then the direction will be changing. But since the body is translating, that is moving in the straight line, then it's not changing direction. So, and velocity has magnitude and direction. Therefore, VB is equal to VA, acceleration. So when we take the time derivative of the velocity equation, that yields similar relationship between instantaneous accelerations of the 2 points A and B. So A B is equal to AA, that is the velocity, the acceleration at the point B is the same as acceleration at point A. So the two equations indicate that all points in a rigid body subjected to either rectilinear or curvilinear translation move with the same set, with the same velocity and acceleration. The condition is the 2 points or the rigid body, they are only moving in rectilinear or curvilinear translation. They are not rotating. Rotation about a fixed axis. When the body rotates about a fixed axis, any point P located in the body travels along a circular path. So let's now look at angular motion. Since a point is without dimension, it cannot have angular motion, but a line can have angular motion. Only lines or bodies undergo angular motion. For example, consider the body shown in the figure and the angular motion of a radial line R located within the shaded plane. So this is R. So it can move round. R can move round. This point, this is from O to P is R. So this line can move round. And as it's moving round, it's forming this disk. Angular position. At the instant shown, the angular position of R is defined by theta. Is defined by theta. That is, the point R, you have to have a reference line. So since R is a line, then you must have a reference line. If P is a point, you must have a reference point. So the reference line is here. This is the reference line. So R now has a position and is theta radians away from the reference line. So at the instance shown, the angular position of R is defined by the angle theta measured from a fixed reference line to R. So this is the fixed reference line to R. Angular displacement. Angular displacement is vectorial, while position is scalar. The change in the angular position, which can be measured as a differential z theta, is called the angular displacement. So from here now, which is the position, to this point, that's we're talking about line R, the angle is z theta, a small change in theta. So that's the angular displacement of R. The vector has a magnitude, the theta, measured in degrees, and then where one revolution is 2 pi radian. So the angle, the theta or theta, can be measured in radians, in degrees, or can be measured in revolutions. So since motion is about a fixed axis, the direction of the theta is always along this axis. The axis is this point O. So specifically, the direction is determined by the right hand rule. That is, the fingers of the right hand are called with the sense of rotation, so that in this case, the thumb or the theta points upward, as in here. So the direction of the curving of the fingers shows the direction of the rotation, which is counterclockwise. In 2 dimensions, as shown in the top view of the shaded plane, both theta and the theta are counterclockwise or anti-clockwise. And so the thumb points outward from the page because we're looking at the page, and then the the movement, the motion is counterclockwise. Then the thumb is like putting, uh, piercing this page with a biro, and then the direction outside, out, is the direction that they are talking about. But the motion is counterclockwise, anticlockwise. Angular velocity. The time rate of change in angular position is called the angular velocity omega. Since the theta occurs during an instant of a time, dt, then omega is the theta dt. And then the direction is anticlockwise. The positive direction, sorry, is anticlockwise. This vector has a magnitude which is often measured in radians per second. It is expressed here in scalar form, since its direction is also along the axis of rotation. So the axis of rotation and its direction, they are the same. So when indicating the angular motion in the shaded plane, we can refer to the sense of rotation as clockwise or anticlockwise. But if you refer to it as clockwise, you must be consistent in your calculations. Here, we have arbitrarily chosen counterclockwise rotations as positive and indicated this by the call shown in the parentheses here in this bracket. Realize, however, that the directional sense of omega is actually outward from the page. Angular acceleration. The angular acceleration alpha means the time rate of change of the angular velocity. The angular acceleration alpha measures the time rate of change of angular velocity, that is the omega dt. The magnitude of this vector is alpha is equal to the omega dt, and it is anticlockwise, is positive anticlockwise. So it is also possible to express alpha as d2 theta dt2, that is the second derivative of angular displacement. The line of action of A acceleration is the same sense as that of omega. However, the sense of direction depends on whether omega, that is the angular velocity, is increasing or decreasing. If omega, the angular velocity, is decreasing, then alpha is called an angular deceleration and therefore has a sense of direction which is opposite to omega. By eliminating the t from equations 1 and 2, we obtain a differential relation between the angular acceleration, angular velocity, and angular displacement, namely that we know that one, angular velocity omega is the theta dt, and we know that alpha is equal to the omega dt. So here dt is equal to the theta over omega, and here dt is equal to the omega over alpha. So we can combine, because now we have the t, the t. So the two of them can be equated. Then we now have that the theta over omega is equal to the omega over alpha. So which will give us alpha the theta is equal to omega the omega. So the similarity between the differential relations for angular motion and those developed for rectilinear motion of a particle v ds dt, which we have done in the earlier class, a v is equal to ds dt, a is equal to dv dt, and a ds is equal to v dv. Here, a, acceleration in rectilinear motion, is alpha in our angular motion. The theta is angular displacement. The s is linear displacement. V is velocity. That is linear velocity. While omega is angular velocity. So this guy here, ADS is equal to VDV, is similar. It is for rectilinear motion, while alpha d theta is equal to omega d omega is for angular motion. Constant angular acceleration. That is when acceleration, when rate of change of velocity is constant. If the angular acceleration of the body is constant, A is equal to AC. The subscript C stands for constant acceleration. Then all the equation, when integrated, yields a set of formulas which relate the body's angular velocity, angular position, angular time. These equations are similar to the equations we have developed for rectilinear motion. And these are the equations that we say the three equations of motion, the Newton's three equations of motion. So for the linear motion, we have similar to this. This first equation is omega naught plus alpha c t. The similar one for our for rectilinear motion is v is equal to u plus at. Then this one is s is equal to ut plus half a t square. And then the third one is v square is equal to u square plus 2as. So, and this is for rectilinear, that is linear motion. And this is the similar equations for rotational or angular motions. So here we say omega is equal to omega naught plus alpha c. Omega naught is the initial angular velocity, while omega is the final angular velocity. Theta, that is displacement, is theta naught, which is the initial displacement, plus omega naught t, that is initial angular velocity, plus half alpha c t square. Then omega square, the final velocity, is omega naught plus 2 alpha c theta minus theta naught. Theta naught is the initial position, while theta is the final angular displacement. So this is only useful when you are looking at constant angular acceleration. So motion of point P. As the rigid body in figure C rotates, so as the rigid body P, this point P, travels along a circular path of radius r with the center at point O. So the path is contained within the shaded plane shown in the figure here. So this disk was just brought out here. So the position and displacement. The position of P is defined by the position vector R, which extends from O to P. So if the body rotates the theta, then P displaces the S, which is R the theta. Velocity. Velocity of P has a magnitude which can be found by dividing the S is equal to R d theta by dt, so that we have V, the S dt is V, the R d theta is, R d theta dt is omega R. So V is equal to omega R. The S dt is equal to R d theta dt. So that will now give us V is equal to R omega, V is equal to omega R. So as shown in the figure C and D, the direction of velocity V is tangential to the circular path. It's tangential. So both the magnitude and direction of V can also be accounted for by using the cross product of omega and RP. That is omega cross RP. Here, RP is directed from any point on the axis of rotation to P, to point P. We have that V is equal to omega cross RP. The order of the vectors in this formulation is important, since the cross product is not commutative. That is, omega cross RP is not equal to RP cross omega. Omega cross RP is not equal to RP cross omega. Notice in figure C how correct direction of V was established by the right hand rule. We have done that. The fingers of the right hand are called from omega towards RP. That is omega cross RP. The thumb indicates the correct direction of velocity V, which is tangent to the path in the direction of motion. The magnitude of V is equal to omega RP sine phi. That is the angle between the vector or the velocity and the position vector RP. So V is omega cross R. Acceleration. The acceleration of P can be expressed in terms of its normal and tangential components. Since A subscript T, that is the tangential component of acceleration, is equal to dv dt, and the normal component is v squared over rho, where rho, that is the radius. We know that V is omega R and A is the omega dt. Then we have AT is alpha R. That is when you differentiate your velocity with respect to time. and your velocity is omega r. So then the omega dt is alpha a, and then you still have your r. So in essence, what we're saying is this. You have your acceleration is v, sorry, dv dt, which is equal to the omega r dt. So, and the omega r is alpha, then r. So your A is equal to alpha r. That is, this one is tangential acceleration. So, and the normal one, the normal component is omega square. So we know that alpha A is that is an is v square over rho, which is equal to omega square r square over r. So this one cancels out, which is equal to omega square r. The tangential component of acceleration in figure E and F represents the time rate of change in the velocity's magnitude. If the speed of P is increasing, then AT acts in the same direction as V, as velocity. And if the speed is decreasing, AT, that is tangential acceleration, acts in the opposite direction of the velocity. And finally, if the speed is constant, tangential acceleration is 0. So this is the graphical representation of the two components of velocity. The normal velocity is always directed towards the center of the curvature. It's always directed towards the center of the curvature, while the tangential is always tangential to the path of the velocity. So, and then A is the vectorial summation of the two components. The normal component of acceleration represents the time rate of change in the velocity's direction. The direction of normal acceleration is always towards O, towards the center, and that is the center of the circular path, or towards the center of the curvature. So, like the velocity, the acceleration of P can be expressed in terms of the vector cross product. So, taking the time derivative of the equation, we have that A, that is acceleration, is the v dt. And we know that our v here is equal to omega cross rp. So we now apply product rule to it. We first of all differentiate omega, that is the omega dt, cross rp. Then we now hold omega, and then we now differentiate rp. So I'm recalling that the omega dt, this guy is alpha, and then the rp dt is equal to v here. The rp dt, that is, this r is displacement. So time rate of change of displacement gives you velocity, which is v cross rp. So this guy again is coming out to be two components. So it's going to be something like this: d dt of so the r dt now is omega. Sorry, is omega. So this component will now be omega cross r cross rp, because that's the result of this, the RP dt. So it's now going to, the RP dt will give us two components. So A now will now be alpha cross RP. This component, this is alpha, this RP, then plus omega cross, this guy is omega cross RP, as shown here. So we now have that when we do the triple cross multiplication of this omega cross RP, we now have that A, the total acceleration, is alpha cross R minus omega square R. So the tangential acceleration and the normal acceleration are perpendicular to one another. And if needed, the magnitude of acceleration can be determined from Pythagorean's theorem, which says that at squared plus an squared root of the two will give us that acceleration, the magnitude of acceleration we are requiring. Thank you. This is end of part A. Do not forget to like my videos, to subscribe to my channel, to share my materials. Then please, if you have not done it, press the notification bell for new videos. If you are one of my university undergraduate students, please do not forget to subscribe with your real name. Thank you.